Hi, folks. Welcome to be here. Thanks, everyone, for coming. So show of hands, who is new? Who is repeat? All right, good mixture. All right, well, for those of you that are new, welcome. And this is our May Meetup. We're almost halfway through the year, kind of crazy. The first question we always ask at this meetup, and we're getting really bad responses the post-pandemic, who's hiring? No one is hiring, like ever. Okay, well, just in case someone is hiring and is watching virtually, you can go to the nyhackr Slack and post a job there. If you're already a member, it's nyhackr.slack.com. Or if you're not a member, if you go to nyhackr.org, that's our meetup website, you will be able to find a link to join the Slack. In there, there's a channel called Job Postings. Post your job in there. If you're looking for a job, go there and see what people post. People post in there occasionally, more frequently than they do in person. So if you need to find a job, go to Job Postings. Pre-pandemic, there'd be like 5-7 people here hiring at a time. So we need to reverse that and get people more jobs. So if you're in a hiring position, hire. On to hopefully more optimistic things. The pizza. Those of you that are new, you're not aware of this yet. Paul, thank you. I see you're already reaching for your phone. The pizza today, come on, Eric. The pizza today is from Grandma's One Pizza. It's a new spot we just discovered. So everyone, go to your phones, go to bit.ly/pizzapoll, and rank it on our 5-point scale. Let us know how it is. Those of you that have been here repeatedly know we've been doing this for about literally over a decade. Not plural, though, because we've only existed for 16 years, and we didn't do it for the first 2 years. So we got like 15 years, not including the pandemic. Including the pandemic, I guess. So yes, but almost decades. Thank you. So go there. There's a crucial data set underpinning society. Without this data set, it all falls apart. So everyone in the room who ate the pizza, go rank Grandma's One Pizza. Those of you that are attending virtually, I know you can't eat our pizza. Hopefully you're eating pizza. Let us know. If you're eating pizza, you're having something else to eat, or if you're not eating at all. There's 2 ways to comment. You can either go to that Slack channel that we mentioned before, nyhackr.slack.com, and go to the monthly meetup chat channel. Or if you're in the YouTube chat, you can comment right there, let us know what you're eating. Vikram, I don't know which part of the world you're in right now, but Vikram usually tells us what he's eating. So let us know, Vikram, since you're not here. But yeah, let us know. Grandma's One Pizza. Vote on it if you're here. If you're not here, tell us what you're eating. The June meetup is theoretically roughly scheduled. We're just waiting for some confirmations. So we will announce the June meetup later. Sit tight. You'll get that information. August. Kevin, are you speaking in August or?
July.
July. It's only May. July is right there. Thank you for speaking. What's your topic?
Geospatial differentiation of homeowners insurance rates.
There you go. All right, say it again 3 times fast. All right, but it'll be a geospatial insurance talk, so everyone's going to really enjoy that in July. Awesome. All right, cool. And then we'll do more announcements as we get them coming. Some of you may have seen a save the date for the New York Data Science and AI Conference. For those of you that are wondering, that looks a little bit familiar, this is a continuation of our wonderful conference we've been putting on for 10 years. Just time for a little bit of a refresh. So if you tickets are not on sale yet. The speaker lineup is not fully set up yet. But if you go to dataconf.ai, you can find more information. It will be in the end of August, which I know is a rough time in New York, but it's a great time for when venues are available. So we'll be holding it then. If you want to give a talk, come say hi to me if you're at the meetup. If you're not here at the meetup, if you're virtual, go to dataconf.ai and click the button to submit a talk. All right, we're doing a little bit differently this year. We're actually taking submissions, and it'll be really exciting. It's going to be a 2-day conference with a day of workshops, and we're really excited for this new refresh of the conference. So dataconf.ai to find out more. I want to thank George, who is not here at the moment, for getting us this space once again. George is our hero, always getting us space. I want to thank NYU, particularly the Prism Center, for hosting us for, is it 1.5 years or is it 2 years? Many months they've been hosting us. We want to say thank you to NYU and George particularly, who's like the mastermind getting us this space. So everyone, he's not here, but round of applause for George. He'll watch this. So what I also always ask George is, which bar are we going to go to? For those of you that are new, we always have the pizza, which you already ate and you already voted on, right? Everyone here voted? Good, good. Then we have the talk. Then we're going to go to a bar. We've been going to Malt House the past few times. Maybe today the night weather's nice. Maybe it's Vol Denis, maybe White Oak. At the end of the meetup, I will tell you what bar we're going to go to based on popular demand and what I find in Google Maps. And if you're watching virtually and live in the city and want to pop into the bar after the talk, people have done that, come by, I'll announce it afterwards. So hang around for that. Paul, are you coming this time? Oh, Paul. Don't let Paul leave, okay? That's the deal. All right, so with that, next month we'll announce shortly. No one is hiring. We all voted on pizza. You are going to come to the New York Data Science and AI Conference in the end of August, and you're going to come to the bar afterwards. And by the way, just because you're going to the bar, if you don't drink alcohol, that's fine. They have non-alcoholic beverages. They have food. Just come and hang out and chat with us. We're cool to hang out with. Said not my wife to me. No, but I met her here, so that's the joke's on her. All right, so that up, we are going to introduce our speaker coming to us with an illustrious talk about orchestrating AI. Everyone, please welcome Donny. Let's check your mic.
Portnoy's got nothing on the pizza ratings here. This is an amazing meetup. It's been going on for a very long time. I'm just very glad to be here. Because I'm a newcomer and I like to try to tailor things to the audience, could I just get a show of hands who here writes and runs Python for a living? Okay, and who here is using cloud compute of some kind? Okay, and who here is familiar with Kubernetes? Oh, okay. And then lastly, who here is working on machine learning workloads? Okay, all right, cool, that's helpful. I'm going to try to use not so much jargon. I accidentally use jargon at times, so if I do use a phrase that just doesn't click, like, feel free to stop me and ask what the phrase was. This talk is mainly about empowering AI development more than it is AI methods themselves. I give variants to this talk, and I'll go into sometimes I'll go into specifics of the kinds of AI things that people are doing with this kinds of tooling, and I'm happy to go into that just as far as like what I see out in the world. I work with like hundreds of AI ML teams, and so I have like decent exposure. But this is going to be much more actually about like how to get things done as an AI ML developer, or as a person trying to run Python at scale, or just run Python in the cloud at all. Originally, the theme of this talk was about separating orchestration and execution. That will make more sense later. A little bit about myself is I am a co-founder of this company called Runhouse. We work on AI development systems. We specifically work on an execution engine that kind of addresses a lot of the things that hypotheses that I'll introduce in this talk, specifically for facilitating AI development on cloud compute. But my background, I'm the co-founder of this company. I've been working on it for about 2 years. My background is that previously I was the product lead for PyTorch at Meta. I worked with hundreds of ML teams from the extremes of research, the extremes of production, and saw very similar themes pretty much across the board as far as the infrastructure pains of just doing AI development. There's a million ways to run Python on cloud compute, and pretty much none of them are good. And so that sort of was what led me to working on Runhouse and now this system. Before that, I was the tech lead for IBM's open source quantum algorithm software. So my background is actually like research and open source software, sort of swirled around that world, and now practically I do kind of 50-50 of both. All that was also Python, for the record. So I'm going to start with basically kind of the history of what AI platforms have been and why the term AI platform is not very good. Also, I'm going to use the phrase AI and ML interchangeably here just because I like to rile people up, but just take that, I guess, as a speaker's note. The sort of prehistoric version of an AI platform was basically at Google or at Facebook, somebody went and built a really large-scale regression system, and it was way too difficult for anybody to be able to rebuild themselves, and so they sort of exposed it as a service. And if you brought some data, and also they're sort of hilariously similarly named, the one at Google and the one at Facebook, makes you think that maybe there's a little bit of cross-pollination. But if you brought some data and this team had this large-scale regression algorithm, they would train a model for you, and then they would serve the model for you. And that was essentially an AI platform. Pros, it works at large scale. Cons, it only does one thing, and it doesn't really care what you want to do. It does that one thing. And so Facebook decided to innovate on this model, and they introduced a system called FB Learner Flow that made a lot of waves in the ML world. that basically introduced what the ML pipeline as an execution structure. They didn't completely introduce it. Some people say they stole it from Microsoft, whatever. But the point was that a lot of people sort of freaked out when they saw this, and they were like, wow, this is so much more general purpose for doing ML, for building machine learning systems. It allows the ML engineer or the ML researcher to compose this system of many steps together that can then be deployed onto cloud compute at large scale. We need to replicate this, and a lot of companies sort of scrambled to replicate this model. And the basic structure of it is what now is often called an ML pipeline, or a directed acyclic graph, a DAG, which just basically means it's got nodes and edges, but the DAG structure of it actually for the purposes of machine learning basically is not used. So what it is basically, you can think of it as a sequence of steps that are specified usually in code, sometimes in configuration files, that each of those steps is an isolated container. And so the container itself kind of defines a unit of work for each of those steps. And then you can kind of neatly package the whole thing and then send it off to a data center to run your AI algorithm. And it's going to go all the way from pre-processing through training, and maybe pre-training, fine-tuning, evaluation, et cetera, et cetera, et cetera. And this is a big innovation compared to just like, we've got one algorithm and you can choose to call it, or you can go and build your own. And this is very idiomatic ML pipeline code. This is Airflow, and I think that when they built it, they thought that these little arrows were neat. And the cloud providers totally ran with it. The cloud providers were eager to sell AI stuff, and they basically said, great. So Facebook and Google have announced that they use pipelines to define all of their production workloads. And so we're going to go and tell the Fortune 500 that if you're doing production ML, you should use pipelines, because if it's big enough for Google, it's big enough for you, and there's no way you can possibly grow out of it. And then, oh, right, you need to actually build the thing, so we'll give you Jupyter notebooks. We'll steal that from the R community. And that's really what most ML platforms actually grew out of, was a sort of greedy search through the random things that a Fortune 500 company asked Amazon to build for them. And that's why you get these long lists. Oh, there's RStudio, beautiful. You get these long lists of products that sort of just address the individual point problems of building ML systems, but they don't really look like much of a cohesive platform. And then a lot of people grew out of those because they're really opinionated about the AI methods. Often you could get started kind of doing the things that they suggested that you do. Oh, why don't you try fine-tuning a model? Why don't you try deploying a model? Oh, bring your checkpoint, et cetera. And the vanilla sort of happy path is good, but within a year or two, often you start hitting this sort of opinionation, the things that they didn't plan for you to do, and then a lot of teams end up breaking out of that into a homegrown stack. And the homegrown stack looks sort of similar. Generally, it's some sort of sandbox environment where you can do fast-paced iteration, which often looks like Jupyter notebooks. Sometimes it's just everybody can spin up a few EC2 instances and SSH into them, but it's limited in terms of scale, and it's generally pretty stateful, and it's generally not usable in the real stack. The real stack is production, and that's where the scaled compute is, and it's usually hell to use, and it's supposedly stable and reproducible, but it is what I call push and pray development. It has no development loop, right? You execute through deployment. So research to production is a common discussion in this world where you built something, or somebody built something on the research side, and it doesn't scale, and it's not fit for production, and there's actually literally no way to run it in a way that would be able to run on a recurring automated basis, or to expose it to users as an endpoint, or whatever you need your ML system to do. And so then you have either a productionization team, or you burden some poor researcher that didn't get their PhD to be writing Airflow pipelines to translate it into production. And this is a very long and painful process. So let's start actually picking this apart. The first thing to note is that pipelines were never built to be the execution engine for anything, really. Execution as the task of actually running your code. In the data world, the idea was that, well, you had these SQL queries and Spark jobs, and somebody a data analyst or a data engineer actually wrote this and got it working on an isolated basis. And then when they wanted to create this DAG, what they were really doing was stringing working programs together. Each of those containers was a working program. You would be crazy to iterate your program. Let's say you were trying to build one SQL query, you would be crazy to rerun all of the upward queries in the DAG that were then used to generate your one, the data that's used in your one query every time that you iterated it. It doesn't really make conceptual sense. You don't actually use this as the way that you do your development or trigger execution. It's really more for actually stringing things together. So Airflow, Prefect, all these ML pipeline systems didn't grow out of a desire to create a way to imperatively run a program in sequence. The other thing is that in the data world, you also have DAGs that are traced out of code, which means that as the user either runs the code, as the system runs the code, or you do some sort of static analysis on the code, you extract out a limited set of activities that essentially form a computational graph, and then you optimize that. And a lot of ML people thought, oh, cool, if we just force everybody to use DAGs, eventually we'll optimize them, and nobody ever did. So we don't use it for that either. And then the other thing to note is that when Facebook and Google built their ML pipeline systems as the sole way to run ML at scale, it was a very different type of ML than they're doing today. And actually, they've had to significantly walk this back, but they've probably had the hardest. They haven't made much progress doing that. But the things to note are, one, so they were built for basically 2016 big tech constraints. They were built based off of the idea that the data was always going to be the thing that had gravity. So the data was very aggressively sharded in data centers all across the planet. And what you wanted to do is take your algorithm and send it to the data center. Nowadays, that's no longer the case because, well, the second constraint of 2016 was that everything was only on CPUs. And so the compute was extremely homogeneous. And if you just took your ML pipeline as a series of containers and threw it at a random data center and sprinkled it on the compute that was available, it would run. Nowadays, we use accelerators, we use much more sophisticated distributed computing. That is no longer a safe assumption. And also, generally, the thing that has gravity nowadays is not the data, it's the compute. And so the idea that we do this extreme over-optimization of packaging and bundling our programs into these structures, so just in case we can send them off to a data center in South America, is no longer really a practical reality, not even at Facebook anymore. So the other thing is that these pipeline systems, they do many things, actually. They're pretty over-bundled. So you can actually break up the things that they do into 3 categories. The first is just basically scheduling. That's the sort of bread and butter of what they were originally built to do, which is kind of like cron, right? You just need to be able to specify, I want this workload, this series of steps, the sequence of data artifacts that depend on one another to be executed every day or every week, or I want this one to run after this one. And I also want a UI where I can see whether the things ran today and what broke, and essentially cron on steroids. And they do that extremely well. If you could have taken that to the extreme, GitHub Actions is a very essential version of that. But in practice, Airflow is maybe the Airflow or Argo, which is a Kubernetes specific one, is generally relatively, or Argo is pretty scheduling focused. And then another thing they do is asset tracking and lineage. And the idea is that when you're building a data system, actually most of the steps of your computation represent artifacts that are being created, like every SQL statement, or most of these SQL statements are generating tables themselves. These Spark jobs are generating tables, and, or whatever. The data is moving around, and being able to actually have a unified way to track all that is incredibly valuable. And so Dagster is a good example of a system that does that. DBT is a neat way of sort of chaining these things together. And then the last thing, which is the thing that we focus on, is being the actual execution layer into the infrastructure itself. And so that is the thing that I'm going to argue today is a problem and shouldn't be bundled into these other things, because that over-bundling causes a lot of pain and trouble. And there's a sort of gradual spectrum of systems that do that infrastructure. But at the middle is Airflow, right? At the middle is an attempt to do everything. And be kind of the only system that you use to execute any code on your cloud compute, and also to schedule things, and also to track your assets. So these systems are better at some things than others. I mentioned some of them. Cron scheduling, dependencies between jobs, observing failures and progress, what ran today, triggering retries and manual intervention when something breaks, or governance, tracking lineage, et cetera, and just specifying the high-level logical flow of work inside of a company. It's a sort of, an orchestrator can be a workflow orchestrator, or a pipeline orchestrator can be the beating heart of a company in a way, right? It's all the data on a daily basis is sort of getting generated one after another. What they're not great for is iteration. When you need to change anything about your program, if you're writing it in Airflow, for example, You need to rebuild all your Docker images, and then like generally the way that it works in most companies is you push your code up to version control, and then you have some automation that rebuilds your Docker images and redeploys them and then triggers the Airflow job, and that is all a 30 to 60 minute iteration loop. So this is the first exposure we have to the real pain of the production AI step. It's not development, right? 30 to 60 minutes is not a development loop. Debugging is near impossible because when anything fails, all the underlying containers that Airflow was running just completely disappear, right? Like, compared to just SSHing into an EC2 instance, it is incredibly unprivileged debugging. Scaling and distributed is pretty annoying and pretty difficult to wire up because you need to get Airflow to launch collections of containers for you instead of launching one container for you at a particular step. And depending on the orchestrator, that is, you need to wire up distributed communication between those containers and things like that. Code modularity and reuse is generally a huge problem for these kind of orchestration-heavy ML teams because there's a reason in computer science undergrad you learn not to write everything in a gigantic main function because like organizing your code is good. And if everything that you do as an ML team ends up being just like a sequence of steps, then it ends up being just a lot of main functions and a lot of copying and pasting and a lot of forking, and that practically becomes a big problem for a lot of teams. They share almost nothing. And then finally, actually, orchestrators often claim that fault tolerance and retries are an expressed benefit of using them, but actually the fault tolerance is not very good. And this is why you hear so many complaints about like being stuck in like Airflow hell. When it fails, it just fails, and the failures tend to cascade, and it requires a lot of manual intervention, and they're not really very good for fault tolerance from the perspective of the system actually having the ability to build the recourse to adjust to the failure into the system itself. There were dates in here of kind of like when these AI platform waves happened, and then I call this part the scramble, which is when sort of nothing happened. It just felt like everybody was sort of trying to figure out what to do about Gen AI. And actually, the funny thing is that this, I think, is a sort of easy thing to say about 2022 to 2024. But the more interesting thing to say about it is that, one, in a lot of companies, they went from being kind of AI interested and like AI enthusiasts to actually making real money from AI, or I should say ML. Like, there were certain use cases that in 2020 you would find in like an innovation team of a company, and then by 2022 we're like deeply dumb not to do with deep learning. And like good examples like fraud detection. And this is like actually a revolution in many ways because it used to be really hard as an ML person inside of a company. You could be doing great work, but your CFO is always asking like, how justify yourself, right? And then at a certain point there were a lot of things like ranking recommendation, fraud detection, churn prediction, lifetime value prediction, risk modeling. All of them became very understood to be effective with deep learning and actually very competitive. The other thing that happened is Kubernetes. And it didn't actually happen in 2022 to 2024, but what happened was that it became very quietly the de facto standard for execution for ML workloads. And I'm saying de facto from the perspective that if you were on a sophisticated ML team and you had your choice of how you wanted to organize your compute, 95% of the time today it's going to be on Kubernetes. There is obviously still a lot of non-Kubernetes stuff, right? SageMaker, Vertex, Azure ML, all these things are still very widely used. Many of them are just wrappers around Kubernetes. But with the exception of Facebook and Google, almost all of the sophisticated ML teams on the planet are using Kubernetes. And I like to take a bit of time to actually dig into this because I find that most data science ML people are rightfully skeptical of Kubernetes or rightfully reviled by it. And I like to just contextualize why Kubernetes is so ubiquitous and also why it's not evil. So the reference sort of workflow that I like to compare Kubernetes to is just using individual instances in like an elastic service like EC2. Let's say you're starting a new company, you have a cloud account, and you can do whatever you want to do your ML stuff. Most of the time, people are just going to start spinning up EC2 instances. Okay? Once you start doing that, you quickly learn like, oh, this is extremely manual. I basically, every time I need to bring up a new instance to do a new thing, I basically need to make sure the CUDA drivers are set up correctly, install all of my dependencies, maybe like, install my conda environment for the nth time. And if I want to be efficient about how I'm using them, then I'm spinning them up and down often, and it's kind of a huge management pain. And if I'm doing anything distributed, then I need to configure the communication between them, and I need to keep a list of IP addresses, and like, it's actually kind of a huge pain. So if there were a system that allowed me to basically have the same experience of being able to run something on an EC2 instance, but I could just like quickly replicate it and just like do n of them, that would be pretty nice. And if I didn't have to constantly SSH in and out of a bunch of different of these instances, and I had a system that could like automate the activities that were going to get scattered across these instances, that would be pretty nice. And there are cloud services that are sort of like serverless containers in this way, but actually the kind of like least common denominator really, if you're looking towards what is the cloud offering that gives you a sort of scalable EC2, it really is Kubernetes. That is the cloud provider's answer to that particular problem. The answer to how you get your applications on there are containers. That tends to significantly improve the reproducibility of the actual setup itself, and it makes it generally easier when you're onboarding a new team member. It makes it generally easier to get them up and running if they're basically following a Kubernetes-centric workflow for setting up their environment versus EC2. But the thing that I'll notice, you can also run Docker containers on EC2 instances, but a lot of companies who build tooling for infrastructure have chosen to build the tooling much more aggressively against Kubernetes than they do for just like running Docker in isolation. Case in point is NVIDIA. A lot of people have struggled with NVIDIA drivers for a very long time on EC2 instances. On Kubernetes, it's just pretty nice. NVIDIA has just invested way more heavily on making things nice in the Kubernetes world than in the just kind of isolated Docker world. The declarative structure is, I don't know, love it or hate it. There are some things that are good about it. Some of it is just, I don't know, a little bit messy and can get cumbersome, but there are a lot of people who love it. The second positive thing about Kubernetes is scalability. And if you're basically thinking, well, I have this cloud account and it has access to this gigantic pool of compute. Why am I going and like still allocating individual servers like it's 1995? Kubernetes is also essentially the answer to that. The cloud providers have built auto-scaling capabilities, like practically any of the auto-scaling capabilities that you might want out of a cloud are built into Kubernetes and not built into the EC2 equivalent. Kubernetes is very richly designed around the idea that you request the resources that you want, and then the cloud provider furnishes the resources underneath. So you need more stuff, and then they add a bunch of instances. You need an ingress, meaning you need a URL that is available to the public, and you're not exactly sure how to do that safely. You can do it through a Kubernetes-centric workflow, and the cloud provider will sort of slot in an ingress behind it. There are different ways that the cloud providers have kind of been forced to fall in line and provide a consistent, automated sort of cloud experience underneath Kubernetes, but most important is scalability. If you're doing like distributed training, hyperparameter optimization, auto-scaling inference, data processing, these things that you just have this gut feeling like, I'm doing this on one machine, and wow, if I had 4, it would go like at least 3x faster, not 4x, but much faster. Like, this is there to scratch that itch. Unfortunately, it's just too painful to do today that most people don't bother to distribute when they don't need to. Scheduling and fair sharing of resources is way richer on Kubernetes than you're going to get anywhere else, or get on EC2. And just like sharing a pool of compute is a workflow that Kubernetes was explicitly designed around. And like bin packing your jobs into a pool of compute. Portability is super important, being able to move between clouds without reasoning about the difference between the EC2 API and the GCE API. And then even just portability across research, dev, staging, production. Kubernetes is going to be identical in all those cases, versus if you have, Jupyter Notebook kind of like instance running on like a beefy, Jupyter Notebook running on a beefy EC2 instance. That instance was set up at some point in time. And then if your production stack is some other instances, those are also set up at some point in time. Especially when like GPUs are expensive and people like to shop around, this has actually turned out to be one of the biggest forcing factors for why people execute on Kubernetes. The ecosystem around Kubernetes is incredibly rich. It's like basically the place to build observability and monitoring and DevOps tooling. And that's probably the single greatest force behind ML teams broadly adopting it is that actually their infra teams generally force them to. And it's because if you want to configure network rules or security or sharing or even just like the relationship between the usage of the resources and the kind of cloud billing or the cloud security concepts, all of that is super rich. And so usually it's actually an infrastructure team that much prefers to be managing Kubernetes than whatever other kind of crazy ML platform the ML team wants to bring in that has a less horrific dev experience for ML. So the other sort of side benefit of this is that if you have an ML platform team and they're managing some sort of like extremely vertical specialized piece of like ML equipment, like a different kind of ML platform, you're dedicating resources to that theoretically your main platform team that supports Kubernetes could just be directly supporting you and resolving things very quickly because they're experts, whereas SageMaker, for example, or whatever, is generally very poorly understood relative to how well understood Kubernetes is. I'll just briefly note Slurm because we are in a place of high education. The thing about Slurm as a way to share resources is that it's like really nice for like the speed of iteration, especially compared to Kubernetes. But it is really bad at a few very important things for enterprise. Not for academia. It's great for I think most academic and HPC work purposes. It's really bad for fault tolerance. This is why so many people have like trauma from grad school babysitting Slurm jobs. Because when anything dies, like a single process, a node, flea hiccups on a server, and like your job ends at 3 o'clock in the morning. And that just doesn't work when you're running trainings on an automated basis. It's not so good for heterogeneous compute. It's really designed around the idea of having very homogeneous compute. And then most problematically, it's actually really not reproducible because it's so stateful. Generally, Slurm works with a shared file system underneath all of the nodes. And that's the way that you can get this like super fast iteration loop between your like individual box and like the scaled compute. But that statefulness is really problematic in like an enterprise environment where a lot of things are happening because it's very hard to reproduce things, and you can do something that has side effects on other people's work. So all those benefits of Kubernetes are really nice. The catch is that it just sucks. It's just incredibly unpleasant to use as an ML developer. And there are a few reasons for that. And they relate to why ML development is very different from software development. The first reason, and I like to be very precise about this because I think that ML has a long history of vendors just kind of claiming that AI ML is special and that's why you need to buy my thing. I don't think that AI ML is special. I think it's different in very specific ways from regular software development. Everything else should be exactly the same other than the implications that flow out of the things on this slide, if I'm correct. First, and probably most importantly, everyone else has local development, generally. That is usually the case when you are a software engineer of practically any other kind. You're a front-end engineer, you can build and iterate your application locally, and then when you're done building it, you can deploy it and then see how it looks. But it's very much a deploy when it is already working kind of workflow, and the same is true for if you're a back-end engineer building microservices or a monolith, whatever that is, you have some semblance of local fast iteration. In ML, we just generally don't have that. If you're using relatively small data on CPUs only, then often you can do things on a laptop, and that's great. But nowadays, most teams end up wanting to be able to use GPUs or distributed compute or larger data than fits on a laptop, or even just they have data restrictions, like they have data residency restrictions, or they have to actually like leave things in the cloud because you shouldn't load lots of user data on your laptop, turns out. So that's one of the biggest restrictions that makes ML development different. So you can see why a system like Kubernetes, which is extremely neatly packaged, everything is a container, doesn't really work so well for that, because if you're trying to remotely develop on Kubernetes, then every time that you want to make a single code change, you need to rebuild and repush, and that's 30 to 60 minutes. It's the same workflow that I mentioned that makes Airflow very painful to iterate and debug. Also, that kind of ephemeral compute problem where like anything that fails instantly disappears, and you can't just like SSH onto debug or like port forward to view a dashboard of some system that you're using. That tends to be exacerbated on Kubernetes, and that's because Kubernetes is really aggressive about spinning things down that it doesn't think you're using. Availability and efficiency matters a lot. So compute tends to be very multi-region and multi-cloud. To access GPUs at whichever price is available, and just many companies are like multi-cloud now. And Kubernetes is really built for like a single region, single cloud, single availability zone mainly like single region kind of usage pattern that can cause some problems when you want to like run this thing on your CPUs in AWS, but then you bought some cheap GPUs from, I don't know, some cloud like repackaging, Bitcoin mining equipment in Russia or something, and then you want to run the rest of your workload back in the US. So those kinds of things don't work. And then the mixture of online and offline activities actually is a little bit unique in ML, or unique to ML. So in ML, you have offline activities, which are things that happen not in the critical path of a user, like making a request to your system, like data processing and training and evaluation, et cetera. And then those often mix in a funny way with online activities, which look a little bit more like traditional web serving, which is like a user makes a request and it hits your system. So the mixing can sometimes be a little bit difficult to reason about, and that's actually one of the reasons that these workloads don't fit so well into Kubernetes, which is really very good for web serving, but not as good for offline. It's a little bit of and mixing the two is sort of a weird fit. So why this matters is that if you're just a regular AI ML developer that's just trying to get some code run, based on everything I've told you so far, you don't have a lot of great options, right? You're either sacrificing scale or reproducibility or just like time and manual labor, or you're taking on this horrific dev experience. The notebooks and pipelines path actually seems to make a little bit of sense in light of all the things that I've mentioned. And they're really, arguably the biggest problem of all is that most of the tooling that's designed to fix this for you is very opinionated. It's opinionated about something. It's opinionated about that you run your code in their special IDE or their special place that you run code, or you adapt your code to their very special way of launching a training job, or you can only run on their cloud to have like their nice experience. There's a lot of opinionation. And the worst of it is AI opinionation, because when you hit that and you realize like, oh, I've now hit AI methods that the people who built this didn't account for, then you kind of know that your days are numbered in that system. So, but probably the most pernicious of this is the development loop, in my opinion, right? Because that slows everything down by weeks, right? And you have this research to production problem that can take months. Also, everything in Kubernetes is done with YAML files, which just kind of annoys me as a Python engineer, but like that's just kind of personal preference and training. So changing gears a little bit in light of all this, talking about notebooks and ML pipelines and talking about Kubernetes as kind of the standard, what would make a great AI platform? I look to the OLAP databases like Snowflake and BigQuery as sort of inspiration for what a great platform does. So just so I'm really clear about language, I think of DevOps as opposed to platform engineering in the following way. DevOps is basically the sequence of activities that you do as an engineer to take your application that you were building locally in some sort of dev experience and to productionize it. And the DevOps wave was largely one of human process. It was like there was a team that helped you do that, and everything was kind of bottlenecked on the team. And the philosophy of platform engineering is that it should be self-service. You should thoughtfully devise the tools that you give to the people building the systems so they don't need to be bottlenecked on a single team. I think that the OLAP database did that extremely well. Before Snowflake, Redshift, BigQuery were around, if you had a SQL query and you were a data analyst and you could run it on one machine, then everything was fine. But if you had to run it on multiple machines, you needed to do infrastructure. You needed to have a team managing a Hadoop cluster. You needed to learn how to conform your query to be able to run on that cluster. It was a very complicated business, and not that many people who theoretically know SQL today could really do it. After Snowflake, you can run the craziest SQL query and command massive compute as a data analyst, just sort of ChatGPTing SQL in a way that probably would scare people back then. But it's the standard, and it's great. It democratized large-scale data analysis at most companies that adopted these kinds of systems, and it's basically completely self-service. And it gets managed by an infrastructure team behind the scenes to make sure that things are allocated correctly, permissions are right, things are pre-configured so you don't like trip over stuff as a data analyst. And this to me is like a really magic experience for democratizing access to compute to an audience that's just trying to get their work done, trying to run queries and do data analysis. So what I believe should make a great AI platform, if you think of BI and data analysis, the stuff that a data analyst is doing as mobilizing data for the purpose of strategic decision making, AI/ML is the same thing, but it's mobilizing that same data or mobilizing data for the purpose of improving product, right? You're not taking the data You're not taking the Uber pricing data to come up with a strategic decision. You're taking the Uber pricing data to build the pricing algorithm. But it's a data mobilization problem, and you need scale. So the first thing is a great AI platform makes heavy computation accessible and reproducible without opinionation about what methods you can or can't do. Because by definition, AI is an optimization discipline, it's a research discipline, and if you can only do the things that somebody already thought you might want to do, then you're fundamentally limited in what experiments you can run and what discoveries you can uncover. The second is that it should introduce a standard that can be shared by both research and production. If you have a research to production process, you're introducing months, and I believe that good ML, AI engineers and researchers are like goldfish. They just basically grow to the size of the tank that you put them in. And so if you give them a notebook as the place where they can actually do their work, the applications are only going to ever get notebook big. If they can run applications on the scale of the compute that you've actually allocated or bought for them, then they will run faster, right? Everybody, a lot of the time I say this, people say, well, I don't know if I need distributed training. Well, it's like you're running a training, or you're running like a hyperparameter suite, and it could run 10 times faster, and it would cost you basically the same amount of money. You would probably pick to do it, right? The same is true for the people who are running SQL queries, whether they thought they needed distributed SQL or not. Everybody's happy for it to run faster. So if it were easy to run it faster, many people would, but they don't want to have to basically have this conversion process from research to production. That's another important distinction. And then it should make it simple to propagate wins throughout the team. So when you build something, it should not be the case that when you finish your process of taking your thing you developed in a notebook and getting it into production, that 95% of the human processed work that went into that just sort of evaporates into thin air. So it should be captured in code, in my opinion. So our answer to all this is a system called KubeTorch. We're very early stage. KubeTorch is not public. It's basically like a private beta right now. But I like to introduce the concepts because it's basically sort of our attempt to square all these problems together. And it's basically for infra people who love Kubernetes and ML people who don't. And we try to make that a positive by saying for people who like PyTorch, but it's really not in any way PyTorch specific. It's meant to be sort of an answer to Kubeflow. Kubeflow is like SageMaker basically for Kubernetes. It's kind of a grab bag of tools, a notebook, a pipeline system, an inference system. And our answer is, but it's very Kubernetes centric. It has very poor iteration, and it's unfamiliar, and you need to upskill a lot to be able on Kubernetes and Docker to use it. So KubeTorch is to Kubeflow as PyTorch is to TensorFlow, if that analogy is meaningful. TensorFlow makes you write DAGs in kind of like a high-level system, and then you submit the DAG to the execution engine, and if it breaks, it's very difficult to debug. PyTorch basically allows you to just write Python, and it runs the way that regular Python runs, and you can command your GPUs in PyTorch in a much more familiar way. The APIs are pretty clean and modular. There's not that much to learn around. You don't need to learn different APIs for inference versus training, at least very much. It's eager, meaning it just runs the way that your code runs locally, and it's debuggable, and it's general purpose. It's agnostic to the AI methods that you might want to use, and it has a pretty rich ecosystem underneath it. So the idea is basically that KubeTorch is like a Pythonic, eager mode orchestrator. Like if you were thinking of Airflow as just a series of steps that you could run, imagine if you could do the exact same thing from inside of just regular Python, and it would just like magically command the Kubernetes compute around, or maybe a little bit more accurately, just almost bring them to your laptop for you to just sort of like utilize on the fly. So the idea is that you can just use regular Python to define the compute that you want, and you can even do distributed. It'll scale up your code if you say, I want to run this Python on 10 GPUs instead of 1 GPU. It will handle all the execution. The iteration needs to be crazy fast. It needs to be about as fast as a notebook. Otherwise, people still need to fall back to notebooks to be able to get things done productively. So we aim for about like a 2-second iteration time, like to be able to execute something and for all of your changes to propagate to all the cloud resources. Everything should just basically be familiar as far as like being Pythonic. And then everything that's happening in production should basically be identical to how you develop it. And it should be completely unopinionated. It should be agnostic to your choice of cloud or tools or methods or whatever. So the idea is basically just like in PyTorch, you have some function and you want to specify. In PyTorch, you say, I want to run this function on this GPU with this like .2 interface. So we do the same thing, but for essentially arbitrary cloud compute. And we use Kubernetes for the reasons I mentioned earlier. It's the least common denominator, super scalable, super observable, reproducible system that just represents sort of a general purpose way of like grabbing cloud compute from any cloud or on-prem, but doesn't really matter that much if you're just trying to get your work done day to day. So you just basically take your function and you say, I want to run it on a GPU, and I want to use this image to run it on, and that specification of what resources you're going to use is very flexible. You can say, I want to run it on an A100 or a T4, or I want 32 CPUs, or I want X amount of RAM or disk or whatever, as it should be. It should be relatively simple to just say what compute you need out of your cloud account. And then you can also just call .distribute. And then that distribute method basically will just replicate that compute n times, and it will connect to distributed communication if you need it. So in this case, I'm saying I need PyTorch distributed communication, but I could use Spark or Ray or any other kind of distributed communication. That is one thing that we had to manually build into the system, right? So you could call it not completely Python generic, but and then we do basically the same thing for kind of more inference-centric use cases. So this one's a little bit more like you can envision an ML pipeline that can just do these things on the fly, and then now you don't have to translate into Airflow. You can just, as you're running through normal Python code locally on your laptop in a notebook or in an IDE, and just say, okay, I want this to run on these GPUs, I want this to run on these CPUs, and it will just run through. And then for inference, we find that people like this decorator-based workflow a little bit better, where it's like my class or my arbitrary like Python function or class, I can just decorate it and then call kubetorch deploy, and it will just instantly deploy them to Kubernetes as like services with auto scaling or with distributed or whatever you like, and then you can actually just import them and call them as is. So it feels like regular Python, but it's commanding your cloud compute, and that is part of the magic. The other part of the magic, which I'll show you, is the iteration. So this is actually just like a kind of hello world example. It's PyTorch distributed training. It's just basically like an arbitrary training function, like I was mentioning, and it's running a distributed data parallel model, and here I'm just basically specifying the compute that I want to send it to. And if I change anything about my code and I were just using Kubernetes itself or SageMaker or Vertex, it would take me 15 minutes, 30 minutes, whatever, to rerun this code. And because we basically, any local changes that I make, we hot sync them up to your remote resources, you can see the training just like starts. And it's about as fast as, or we're trying to make it as fast as basically running in a notebook. I'm saying notebook, but I'm referring to like a hosted notebook. But really, like if you just prefer to use Jupyter Notebooks locally, it works in Jupyter Notebooks as well. So I think I've already like beaten these points to death. But basically, like there's no difference between the research and production code here, right? If you basically write your code in Python locally and you get it running, and then you wrap it up into an orchestrator node in order to cron schedule it, it runs identically both in dev and in production. So you save all that time, and you never have this like massive productivity hit once something is in production to be able to like manipulate or iterate it. You have dramatically faster dev velocity. The debugging and fault tolerance is much better, so you can like SSH into those resources. Your iteration, your actual debug loop is obviously better. Then one of the neat things about the fault tolerance of the system is that in Airflow or an orchestrator, if something fails, you can't like catch that exception, right? It's like it's a DAG. The DAG doesn't have like, unless the people who built it accounted for this, which many of them don't. You can't just like catch an exception. For us, if your training job that's running in production or locally or whatever hits like an out of memory error, we just propagate it through and run it as like and hand it to you as an exception. You can decide what to do about it. We have users that catch it, tear down that resource, and then just like double the amount of memory and run it again. And they save a lot of money that way. And their like fault rates in production like completely drop by like 97% just because they can catch exceptions. You can follow much better code best practices and modularity. You can use regular version control and CI and testing, et cetera. And scaling and adopting technology is much easier. It allows you to really surgically, inside of any code that you happen to already be running, to say, oh, this function, it'd be really nice if I could use like a bigger model. And actually, I need a bigger GPU to do that, or I need GPUs and I'm not using GPUs, or I need to be distributed, and just very surgically take that one piece and run it on big compute. And so your ability to adopt new technology is a lot better. And where this fits into, like, often the first question we get about this is like, where would this fit? I already have stuff. I already have pipelines. I already have people using notebooks. And we try to design this so it's extremely a la carte and basically just gives you optionality. So one thing you can do is build your entire workflow your pipeline in KubeTorch and then just wrap it in a system like Airflow or a system like Kubeflow pipelines to schedule it because it's just Python. It can be fit into a container in any of those. And then the stuff that you actually do in Airflow itself is very limited. It's just a matter of scheduling it. There's no execution to worry about. You can also leave your existing pipelines in place. And then for the pieces that you need to break out onto bigger compute, you can selectively just adopt KubeTorch in that one little function and just break it out onto large-scale compute. And that's a very a la carte, incremental way to adopt it. And the last thing you can do is for existing pipelines, you can break them out into basically to be running on KubeTorch to kind of restore your development loop without significantly changing their structure. Yeah, so this is what we do. This is kind of my, there are 100 ways to run Python on cloud compute, and they all suck, and so we're trying to build another one, and hopefully it just doesn't become a part of a talk in like 2 months from now, which is about the 101 ways to run Python, and they all suck. But if any of this is interesting to you, please feel free to reach out to me. I mean, we're very early stage, so we're actively taking feedback about the system, and yeah, I'd love if anybody has feedback or thoughts to share. Yeah.
We have time for a few questions before we head out, so ask away. Just do me a favor, repeat the question.
Sure. Yeah.
Hey. Yeah, so I mean, look, you're building this container image, and I mean, a lot of the time is spent installing dependencies. Maybe it takes, multiple minutes to install NumPy or something. Like, I see your code, and you are, at the start of that code, you are provisioning resources, and I don't see how you can have that, that feedback loop be so small, because when you provision those resources, and you're not using like a base image, well, you're not using like a sort of final image, then you are going to have to install dependencies on those resources you provisioned. So I don't even know what the question is per se, but explain to me how that works for you.
So the question is how it's this fast when like you have to like download NumPy, or just like building images is hard. It's a really important question. What I ran there was not the first time that this runs. Okay, this is the iteration loop. The first time it runs, it's going to take a little bit of time. Generally, like this one, which needs like 4 GPUs, took like probably like 3 or 4 minutes just for the cluster to auto-scale to bring me the GPUs. If the GPUs were already in place in the Kubernetes cluster, it'd be probably like a minute or two, because what's happening is that the image that I specified is getting loaded down onto the machine, and then if I layer on additional dependencies, this is like an important point, I can run like pip install and then add like whatever other libraries or add other commands to this image on the fly without triggering a rebuild. And the whole magic, because you can do that in a notebook. In a notebook, if you realize you forgot a library, you don't have to like take down your entire rig and then bring it back up. So we incorporated that too. The magic is basically that we hot sync all these things all the way through. So if I added one pip install there and my resources were already up, then the next time that I ran this, that would get communicated, it would get installed. I would wait the requisite time for NumPy to install in that case, but I only wait once, at least for that development session. And then the hot syncing of the code all throughout your entire application, that's the magic. Yeah.
Oh, that's cool.
Yeah.
As a fellow Snowflake guy, I do appreciate that slide, but the same way, when you have a number of workers, like thinking auto scale, especially it's not just on the training side, but like on the implementation side, where your actual end consumers might need different levels or more CPUs or levels of concurrency. Are you imagining even those would be ephemeral, or would you imagine someone firing up Python to reconfigure this every time?
So is the question about in production how these things auto scale?
Yeah. So like in production, I've done my training, blah blah blah, et cetera, et cetera. Now I know that my system's out there, and I actually want my LLM or whatever I'm hosting to run on GPUs, right? And I need to know that when just one analyst is going there and typing some random question, it's one thing, but then 100 people hit the thing at the same time. Are you letting Kubernetes actually auto-scale that
Yes.
as well?
Yeah, so the question is like our support for auto-scaling. This is a really subtle point. Basically, so we do support auto-scaling. We support every kind of auto-scaling that Kubernetes supports. So we automatically queue up requests in front of your pool of services, and we can scale to 0 if the service isn't being used and bring it back up, all that kind of stuff. The tricky parts are twofold. One is that when you're doing that on the dev side, where the stuff that the user has already done with their application is sort of stateful. It's taken quite a long time to actually make it so that auto-scaling works with that intermediate state. And then the second thing is that in production, we've had to be pretty opinionated that you shouldn't be doing any of this like code syncing in production. Like everything should be frozen in production. When you're doing this kind of dev stuff for training, it's fine. You're iterating your code. You want to hot sync into the containers, cool. But then we have this argument here in the compute class, which is freeze equals true. And what that does is it makes sure that nothing new is getting installed, no code is getting synced. So auto-scaling is going to happen in a much more like standard Kubernetes way. It's much easier to understand and it's much more reproducible.
So just getting back to his question about like the actual images. I mean, obviously, the new node in Snowflake was being spun up. It was the same exact node across everything. It was just there, right? Like ephemeral compute didn't even have to be dedicated to any individual, so you could do that. So, are you when you do that freeze equals true? Is that basically becoming like a binary that just needs to be attached to a compute that can be spun up, or do all those install cycles go in play?
Well, basically, when freeze equals true, it's essentially just exactly the single image that the user told us to start the node with. Okay. Right? So we're telling them, like, you should actually build whatever you're going to use in production, you should properly build it in CI. Same as a front-end engineer, right? If you're going to run a thing in production as a front-end engineer, you should package your application into an image, and that's the one you're going to use in production. We tell people to do the same thing. Yeah.
That's very cool.
Yeah.
Thanks.
Thanks. Yeah.
So what if like a data scientist and I want to do EDA? So I can see how this really works for training. I want to spit something out, run a script, and it'll run through and store artifacts somewhere, right? But what if I just want to do EDA, download a bunch of data, do a bunch of matplotlib plots? Does it make sense for me to like spin up something like over here, and then how do I actually get the visualizations? Does it actually pass like the images through?
Yeah, that's a really great question. The question is like, what would something like exploratory data analysis look like if you didn't have a hosted with KubeTorch? And the answer is like, actually, we're not like anti-notebook people. I think there are a lot of people who work on these systems that are like, notebooks are dumb and nobody should use them. Notebooks are really great for EDA, education, visualization, certain types of collaboration, just like quick debugging. They're really good for those things and people should use them. We don't want to like replace any of those aspects, but for things that are like fault tolerance and scaling, et cetera, those we think you should just do in modularity, you should do in like regular code that can be version controlled, et cetera. There's a sort of in-between answer, which is that if you're trying to actually use large-scale compute and you like to work in notebooks, KubeTorch will do that because it's just Python. It will run in a notebook cell. So in your notebook, if like you wanted to just like process a bunch of data in order to like, I don't know, take t-SNEs or something over a large data set and then bring them back into your notebook and then visualize them with matplotlib, KubeTorch is a perfectly reasonable way to take that function that you were going to use to do your t-SNE inference and then just like scatter it on much more compute and make it run faster strictly within the notebook cell. But you know, and then you just delete that. You know, that just essentially gets erased, evaporates when you're done. But for the most part, that's not a workflow that I'm like actively evangelizing. I think people should just use notebooks for EDA because they're great. Yeah.
Maybe
Yeah.
I missed this in your talk or in the script, or this example doesn't cover it, but how does this handle large ETL jobs where you need to create intermediate data objects, write to databases, just output large data frames? And yeah, can you talk a bit about how it might connect to microservice buckets and databases and such?
Yeah, that's an excellent question. I feel like it's the area that like we have an answer to, but like I feel like it could be a little bit richer. The basic idea is that like you can do all the same things from inside of KubeTorch compute as you can do from inside of Airflow. Meaning like Airflow doesn't really take on any opinions about how it loads data or how it writes data, right? You just do it inside of the nodes, right? You do it inside of the task in Airflow. And we let you do the same thing. At the beginning of your training job, just load in your data or start streaming it in. And what we do is make it very easy to authenticate that environment. So if like you were using Databricks and you wanted to stream in batches from Databricks, or you're using Snowflake, or you're using S3, whatever, you should make it so that, we make it so that the compute that you're using remotely, it's very easy for you to allow it to have the same authentication to be able to stream in those batches, because generally if you're working on a laptop, you have generous enough authentication to do that kind of work. It's a little bit of a work in progress from the perspective that Kubernetes has its own role-based access control system, and it integrates with cloud role-based access control system. So there's some things that are really easy and nice, like loading in data from S3 is basically trivial. Reading and writing from S3 is basically trivial. You authenticate the whole cluster, and then it's like pretty easy. Or even if you want to like just create a group of users within your cluster, and then they can access these things but not these things, pretty easy. We have this other kind of funky secrets syncing system that I don't have it up now, but when you build your image, you can actually just specify secrets that you have locally to get synced and applied as environment variables or as mounts in the cluster. So your weights and biases key or your Hugging Face key to be able to download Llama, that all we just basically work through Kubernetes secrets to do. What I don't think we do super elegantly is like, I still think that loading data at a large scale is a little bit of a failure mode. And like, if we made it nicer for somebody who really was just running like a single node kind of training job in a notebook, and they were going to very simply stream in that data, and then now they want to like scale it to 10 nodes, but they're not necessarily thinking about what data is going to which node or like how to do it efficiently and not get it bottlenecked. We don't do anything about that, and I feel like we potentially could. But it's very clean. You can see how it's very clean for us to just basically say like, inside your code is your own business, and you have a file system, you can save things, you can write things. But sort of an intermediate answer. Yeah. Did you have a question too or no?
Do you remember the name of the meta flavor Kubernetes that's like behind Instagram and all that?
Oh, Google's, the meta flavor Kubernetes Tupperware. Yeah. Yeah, and the Google equivalent was Borg, and they're still very widely used. Cool. Thanks, everyone.
Thank you very much. Just before we head out, just a few reminders. I did see someone posted to the job postings channel. So someone virtually, yeah, thanks. Someone virtually is paying attention. So go apply to that if anyone needs a job. Remember, we have June coming up. We need speakers for the fall. So if anyone wants to speak without me pointing and volunteering you, now's the time to come offer. You come say hi or come email us. I see everyone trying to dart for the hallways already. But yeah, seriously, we need more speakers, so come let us know. You're going to speak? There you go. We got a first taker. You could be like September or October. There you go. Raise your hand so Nicole can see you. There you go. All right, we'll come hunt you down. Before everyone goes to the bar, there's a bunch of pizza left. No one's allowed to leave without taking an extra slice with them. Make sure it's fairly... Paul, take a slice of pizza. It's New York pizza, the best in the world, Paul. He's from Connecticut. He thinks they have a different thing. All right, and we are going to go to the bar. I guess we'll just go to White Oak Tavern this time. It's right across the way. So White Oak Tavern will take you with us when we leave. So thank you, everyone, for being here. Thank you, Donnie. Have a great night, everybody. Bye. Excellent talk.